Hey there. What I decided I was going to do was to do these follow along while you read kind of notes. I also am putting online some tutorials from last year that show you how to do some of the basic stoichiometry conversions, but I think that most of you guys have a pretty good grasp of this. I'm going to go directly to your textbook and work out of that. So that way I can point out things that you're going to be seeing along the way and maybe answer some questions hopefully as you go along. So if you take a look in your notes, I'm going to go to chapter 3. I'm going to go to 3.1, and we're going to talk briefly about how they measure the mass of an atom, because it kind of makes sense that an atom is wickedly small, and they didn't have like an atomometer. But one of the ways that we can measure is we can measure things by weighing them. Now, the example they give in the book is they said, what if we had a bunch of jelly beans? And so they got a bunch of measurements here for jelly beans, and each of those is not exactly 5, but when you go down below here, you're going to see that when you average out all of the masses, they average to about 5 each. And why is that a big deal? Well, it's a big deal because if you know that the average of all of the jelly beans is 5, you can kind of assume that each one actually is 5. Now, let's be really clear here. They aren't all 5 grams. But you can make that assumption, and then later, let's say you have 1,000 jelly beans, you can go, well, if there's 1,000 jelly beans and each of them is 5 grams, you can end up with 5,000 grams. And of course, the way I'm writing right now is with 0 significant figures in mind. But this is kind of what they did with taking large numbers of isotopes of a particular atom and then going, oh yeah, so the average of carbon atoms is 12.01. In fact, the number you see in the periodic table often, that 12.01 grams that you see on the periodic table, sometimes you'll see the unit U, and that stands for atomic mass units. Sometimes you even see it as AMU, or formula mass units. We also know them as grams per mole or molar mass. Now, I'm having a little difficulty with the writing here because I'm using this brand new tool. So it's not like my normal, it's a little bit off. But if you can understand these hieroglyphs, just be aware that the number underneath everything on the periodic table is the average of all the isotopes. And we pretend that even though this is the average of all the isotopes of carbon, let's put that this is carbon just in case you want to come back to this later. We pretend that every single individual carbon also has a mass of 12.01, even though in fact it is probably really unlikely that any of them actually do. In fact, carbon, the molar masses, I think, of the carbon 12 are 12 almost exactly, and for carbon 13, it's almost exactly 13 atomic mass units. And so when you average them out, you're going to end up with a lot more 12s than 13s, and so the average tilts towards 12. Now, so let's move on to 3.2. And in 3.2, they actually talk about the tool that they use to measure everything, and that's called a mass spectrometer. And what's kind of cool is if you click on that, I can't right now because I'm in pen mode, it'll actually define for you what it is. But the way they actually measured it is they actually shot these atoms through a series of magnets, and depending on how much they got deflected, they were able to compare the masses of each other to each other. So what they did is they essentially, if you take a look here, it says it's based on carbon 12. And in fact, they defined that as carbon 12 as exactly 12 units. So what they did is they took carbon and they shot it through, and it bent a certain amount. Pretend that this is right in here where it's getting shot through here, and it bends a certain amount. That's terribly drawn. But then they shot all the other atoms through there, and they bent a different amount. So they were able to come up with ratios compared to 12. So if I shot something through and it had a mass of 12, and then something else, its ratio was 1.1 of what the 12 was, you could multiply 12 by 1.1 and get the new mass. And that's essentially what they did, and it's also kind of the shopping cart principle. If you have a very light shopping cart, and you're in Walmart, you can be like, wee, and make a turn. But if you fill it up with a bunch of waters because you think there's going to be a hurricane and then there really isn't, you end up maybe trying to make the turn and you have to very slowly make the turn. And if you compare how much these two things turn to each other, you're going to get a ratio, and then you can apply that ratio to the original math. Now, if that sounds a little bit confusing to you, I'm sorry, but you should be aware of how they actually did this so that if they ever mention it to you, it'll make sense. Also, I want to show you briefly how they got the average atomic masses of things, and if you take a look here, they actually show you with the example I just talked about, which I probably could have waited for just a second. I like how they keep all the notations here. But you see how they said the mass of carbon 13 right here? Well, they know that the exact number by definition of 12 of carbon 12 was 12. But then when they took the ratio of how much it tilted, carbon 13 was 1.0836129, and they multiply that out, and that's why we actually get this very very close to 13 number for carbon 13, although it isn't quite that because they're multiplying it out. So they did this with pretty much everything else. Now what you should be aware of, if you look at the very bottom of the page here, is you can figure out the average atomic mass if you know the percentages of each isotope. So we did this again, we did this last year, but I'm going to review it very briefly right now for you. Let's go down here and look at this exactly. So we're scrolling here to this. And let me get rid of that. So if you take a look here, they tell us that we have that 98.89% of all carbons are carbon 12, and 1.11% of them are carbon 13s, and then the carbon 14 is negligibly small, so we ignore it here. Now, the way we can actually do this mathematically, see it says 98.89% of carbon 12 and 1.11% of carbon 13, their molar masses. That number right there, you don't want to multiply it out. And the same thing when you are like, hey, what is 95% of 70? Well, if you have 95% of 70, the way you figure that out is you make it into a decimal. You go 0.95 times 70, and that number, whatever that number is, that will be 95% of 70. So we do the same thing here. You are never going to do this. That's my little X. You're going to take that percentage and make it into a decimal and multiply it by this, and then you're going to take the 1.111 and make it into a decimal, and you're going to add the two of them together, and this right here should look very familiar to you because this is the molar mass or the formula mass or the average atomic mass that we find on the periodic table. This right here kind of reaffirms what we talked about before, and just to make sure that you feel comfortable with this, they give you a practice problem on this, and I would encourage you guys to kind of go through it. And I also want to point out to you something here because this is kind of a big deal. How they do the notations here matters. So do you see right here, they have the molar mass of one of them, and they have the molar mass of these other, these are, by the way, neon guitars, right? So these are molar masses for neon, and if you look on the periodic table, you can see what the average of all of them is. But if you also take a look here, do you see these are two graphs that represent the relative amounts of neon that you have. See how you have neon 20 right here, 21, and 22. And if you take a look here, if you read it, and it's kind of hard to read for me here because my eyes are bad, but this right here, you can see you have a lot more of the 20 than you do the 21 than you do the 22, and you can see that my thing is not really calibrated very well. This is actually a little bit easier to read. You see how it says it's 91% 20, and here it's 3% 21 and 9% 22. And so when you do the math, and I really encourage you to do the math on this just to practice it out, you're going to discover that and I'm going to close this up, the same exact thing that we did up above is what we're going to do right here. So they tell us that we have approximately 69.09% is this and 30.09% is this for copper. Now they're using a different example than we were using up above, but they even say the ratio per number of atoms. So if they said if you have 100 atoms, do you understand that 69.09% of 100 is 69.09? So if they talk about the number of atoms down below here, and you're like, how do they get 69.09 atoms? Where do they tell us that? It's because they're actually showing us that there's 100 atoms, and per 100 atoms, you have 69.09 of them are copper 63, and 30.91% of them are 65. If you take this, now they decided to do the atoms, and instead of making it a percentage, they at the very end decided they were going to divide by 100. I would suggest that you guys do this. You go 0.6909 and you multiply it by the molar mass or the formula mass or whatever you want to call it, which they gave you in the problem. So that would be 62.93. And then you're going to add that to the percentage, which is 30.91. 0.3091, and we're gonna make it a decimal of 0.3091, and we're gonna multiply that by the 64.93. And if you do that, you're gonna go straight to this number right here, which I kind of encourage you to do. You might want to also practice doing some of these on your own.